Hi students, welcome to the digital chemistry class. Today we shall discuss on a special class of organic compounds, and before going to the topic directly, I want to have a look upon these slides. Now, you see that these compounds are mostly used in our day to day life, but have you ever thought that from which compounds these products or the articles are prepared? Yes, these are prepared from the special class of organic compounds known as the haloarenes. So, today our topic is the haloarenes, and mostly we shall discuss on the classification, nomenclature as well as the preparation of the haloarenes. So, what are the haloarenes? Now, as the definition says, the haloarenes are, the name itself suggests that halo means your halogen and arenes means the aryl groups. So, halogen means it may be the fluorine, chlorine, bromine or iodine, that means any one of the halogen atoms. So, when the hydrogen of the aryl group is replaced by the halogen atom, then you get the haloarenes, and therefore, the definition of haloarene is mostly like this, that is replacement of sp2 hybridized hydrogen atom in an aromatic hydrocarbon by the halogen atoms like fluorine, chlorine, bromine or iodine results in the formation of corresponding haloarenes. You all know that the molecular formula of benzene is, that is C6H6. When one hydrogen of benzene is replaced by any one of these halogen atoms, then you will get the haloarenes, that is the maybe the fluorobenzene, maybe the chlorovenzene or iodobenzene or bromobenzene, basing upon the nature of the halogen replacing the hydrogen of the benzene. So, now the classification. So, if this is the haloarenes, then how the haloarenes are classified? Now, like your haloalkanes, haloarenes are also classified in two methods. The first method or the first category of classification is basing upon the number of halogen atoms present in the molecule or present in the compound. So, that is your monohaloarene if the number of halogen atom is 1, dihaloarene if the 2 hydrogens of the aryl group is replaced by the 2 halogens, and trihaloarenes if there are 3 number of halogen atoms in the molecule. So, common examples of the monohaloarenes are your fluorobenzene, chlorovenzene, bromobenzene and iodobenzene. In fluorobenzene, the hydrogen is replaced by fluorine. You see that in similarly in chloro, bromo and iodobenzenes, they all are replaced by the chlorine, bromine and iodine respectively. So, similarly dihaloarene. So, a compound is said to be the dihaloarene means how many number of halogens are there? There are 2 number of halogens. So, your example is given in the slide, that is 1,2-dichlorovenzene. Now, 1,2-dichlorovenzene means that molecule contains 2 halogen atoms. Similarly, in case of 1-bromo-2-chlorovenzene, you see that position 1 is occupied by bromine and position 2 is occupied by chlorine. So, that this compound is an example of the dihaloarene. Now, the third class or the third category is your trihaloarene. If the number of halogen atom is 3, then one example, 1 or 2 examples are given, that is 1,2,3-trichlorovenzene, 1-bromo-2-chloro and 4-bromidobenzene. So, mostly the nomenclature classification of haloarenes is just similar to that of the haloalkanes. So, next one is, that is the classification of the second category, classification of second method of classification, that is how the classification is carried out. Now, like haloalkanes, in haloarenes, the classification is also basing upon the hybridization of the carbon atom to which the halogen atom is attached. So, hybridization of carbon means, you know that in benzene the carbon atom is sp2 hybridized, but when we consider the case of toluene. In toluene, the CH3 group is attached to the benzene nucleus. So, when benzene nucleus, the methyl group is attached to the benzene nucleus, suppose we are interested that the halogen atom is replacing the hydrogen of the methyl group in case of toluene. So, there the carbon atom is sp3 hybridized. So, basing upon this, the classification of haloarenes in second category is mainly on the hybridization of carbon atoms to which the halogen is attached. So, one category is your compounds containing sp2 carbon halogen bond and sp3 hybridized carbon halogen bond, and your haloarenes, that is your chlorobenzene, fluorobenzene, bromobenzene, etc., and also they are under the category of sp2 carbon halogen bond, whereas the benzyl halide, when just the example that I have given, that in toluene the hydrogen is replaced by the hydrogen of the methyl group is replaced by the halogen. So, in that case, suppose the hydrogen is replaced by the hydrogen of methyl is replaced by the halogen. So, that one is an example of the benzyl halide, and if the halogen is your fluorine or chlorine or bromine, then we get the benzyl fluoride or benzyl chloride or the benzyl iodide. So, basing upon this, we are having the different methods of classifications for the haloarenes. So, now the question is that if this is the example, you see the slide, that how in benzyl halide the side chain hydrogen is replaced by the halogen atom. Now, here the side chain carbon is sp3 hybridized. So, this is an example of the haloarenes having sp3 carbon halogen bond. So, now come to the nomenclature. So, this is all about your classification. So, now let us come to the nomenclature of the haloarenes. So, nomenclature of haloarenes mostly carried out by two methods. One is your common name method and another one is the IUPAC method of nomenclature. Now, in case of monohaloarenes, the common method as well as the IUPAC method all are same. That is, for nuclear substituted haloarene like your fluorobenzene, the common name is fluorobenzene, IUPAC name is also fluorobenzene. Similarly, for bromobenzene, the common name is bromobenzene and your IUPAC name is also bromobenzene. But when the case arises for dihalogen derivatives, then there is little bit different in the nomenclature. That is, for common name system, we are using the prefixes ortho, meta and para. So, but in case of IUPAC system, we are using some numerical prefixes like your 12, 13, 14 respectively for ortho, meta and para isomers. So, you see here the some examples are given, that is your chlorobenzene. Compare the common name and IUPAC name. Chlorobenzene is your common name, chlorobenzene IUPAC name is also chlorobenzene. But in case of meta dichlorobenzene, the example that is given in the slide, that meta dichlorobenzene is your common name, whereas the IUPAC name is your 1,3 dichlorobenzene. Similarly, for para dichlorobenzene, when the common name is para dichlorobenzene, correspondingly the IUPAC name is 1,4 dichlorobenzene, and for orthochlorotoluene, that is the common name, whereas the IUPAC name is your 1-chloro-2-methylbenzene, or you may write 2-chlorotoluene, and for ortho-dibromobenzene, when the common name, then the IUPAC name is 1,2-dibromobenzene. So, similarly, you can practice a number of organic compounds or a number of haloarenes for giving the for the nomenclature, so that you will be confident upon your confident upon the nomenclature. So, now till now we have considered, that is how the haloarenes are classified. But what about the reactivity of the haloarenes? We are silent till now, we have not considered whether the haloarenes are reactive or what is its order of reactivity. Mostly the reactivity of haloarene depends upon the nature of the carbon halogen bond. So, what is the nature of carbon halogen bond? In haloarene, the halogen atom is having the lone pair of electrons. All of you know that halogen is when forming a bond with the carbon atom, then it has 3 lone pairs of electrons. Now, these electron pairs present on halogen atoms are in conjugation with the pi electrons of the benzene ring. Now, you know that in benzene there are 3 pi bonds and the halogen atom is associated with 3 lone pair of electrons. So, these lone pair of electrons are involved in conjugation with the pi electrons of the benzene ring. So, due to this, the concept of resonance arises, or we say that due to resonance a partial double bond character developed in case of the CX bond, that is the carbon halogen bond, which was initially the single bond, now it acquires some partial double bond character. And because of this reason, the cleavage of the carbon halogen bond in case of haloarenes is difficult, whereas this partial double bond character is absent in case of the haloalkanes. Why? Because in haloalkanes there is no resonance, but in haloarenes the lone pair of electrons of halogen is in conjugation with the with the pi electrons of the benzene ring. So, that is why the partial double bond character is possible. So, basing upon this development of partial double bond character, the haloarenes are less reactive towards the nucleophilic substitution reaction, because when the cleavage of the CX bond is difficult, then it will ultimately lead to the replacement of the halogen by any other nucleophile. So, that is why they are less reactive towards the nucleophilic substitution reaction. So, this nature of the CX bond is better explained by this resonating structures, as you find in the slide, that in resonating structures you see that due to resonance your electron density at the ortho and the para positions are comparatively more than the resonance than the electron density at the meta position. So, from the resonating structures which are clearly marked in the resonating structures, that negative charge is present at the ortho position as well as at the para position, whereas there is no negative charge in the meta position. So, this indicates that the ortho and para positions are having more electron density as compared to the meta positions. So, this again also it is found that the halogen atom attached to the benzene ring is having the minus I effect or the negative inductive effect, but the lone pair of electron is involved in conjugation. So, that is mainly due to the plus R effect of the chlorine atom, but in addition to that, being the electronegative element, chlorine has the tendency to attract the electron pairs towards itself, as a result of which this attracts or withdraws the electrons from the benzene ring, and since it withdraws the electrons from the benzene ring, this deactivates the benzene ring. So, even though the ortho and para positions acquire the negative charge, in case of chlorobenzene you find that they undergo the electrophilic substitutions, but the substitution electrophilic substitution in haloarenes occur slowly, and therefore, it require more drastic conditions as compared to those in case of the benzene. So, now let us consider that what we have studied till now. Now, we have studied that what are haloarenes, that is the definition, that means when the hydrogen of the aryl group is replaced by the halogen, we get the haloarenes. Then what is your classification and nomenclature of haloarenes? Classification 1 is basing upon the number of the halogen atoms as well as basing upon the nature of the hybridization of carbon to which the halogen atom is attached, and then the nomenclature of haloarenes, that is what is the difference between the common name and IUPAC name method of nomenclature when the nomenclature of dihaloarene and trihaloarene is taken into consideration. And the next we have discussed the nature of the CX bond, which determines that why the cleavage of the carbon halogen bond in haloarene is difficult, why the haloarenes are less reactive towards the nucleophilic substitution, and also why haloarenes undergo electrophilic substitution reactions mostly at the ortho and para positions, but slowly only under drastic conditions. These things are all related to, these three things are all related to the resonating structures of haloarenes, that is, or chlorobenzenes, that is, the negative charge is present at the ortho and para positions. So, that is why they undergo the electrophilic substitution. Due to resonance, carbon halogen bond has partial double bond character. So, therefore, they are less reactive towards nucleophilic substitution reaction. Hello students, now let us discuss the preparation of the haloarenes. Now, haloarenes are mainly prepared by two methods. One is from benzene by direct halogenation method, and second method is from benzene diazonium salt. So, now let us consider the preparation of haloarenes from benzene. Now, basing upon the nature of the haloarene or the nature of the halogen used in the direct halogenation reaction, we have to impose different reaction conditions. In other words, the preparation of different haloarenes require different reaction conditions. For chlorobenzene and bromobenzene from benzene, the normal reaction is they are similar. That means, benzene when treated with chlorine in presence of the catalyst Lewis acid, that is your anhydrous aluminum chloride or ferric bromide chloride, it produces the chlorobenzene. Similarly, benzene when treated with bromine in presence of catalyst anhydrous aluminum bromide or ferric bromide, it produces bromobenzene. So, now let us see the reactions, that is, here is the preparation of chlorination of benzene or the reaction, chemical reaction for the chlorination of benzene. So, whether it is a chlorination of benzene or bromination of benzene, the reactions are an example of the electrophilic substitution reaction, or in other words the aromatic electrophilic substitution reaction. So, the mechanism involved is similar to the mechanism of the aromatic electrophilic substitution. So, what are the different steps involved in the mechanism of chlorination of benzene? Now, like your aromatic electrophilic substitution, the first step is the activation of the electrophile by the Lewis acid. If we are considering the example of the chlorination, you see that chlorine when comes in contact with the Lewis acid, that is aluminum chloride, it produces the electrophile. Now, the electrophile chloronium ion is attacked by the pi electron clouds of the benzene ring. So, that we are getting the aronium ion, and this aronium ion is stabilized by resonance, and the resonance hybrid is given in the slide. Now, the right hand side structure of the slide indicates that that one is the resonance hybrid, and the structures within the square bracket indicates the resonating structures. Now, from the resonating structures you see that the reaction is a slow reaction, and in this structure the carbon atom has lost its aromaticity. Why? Because it is tetravalent, and since it loses its aromaticity, then the immediate step is that it undergoes the deprotonation to restore the aromaticity. So, the aronium ion, which one is stabilized by resonance, now it immediately loses the proton when comes in contact with the nucleophile, that is aluminum tetrachloride, it produces the chlorobenzene. In addition to that, the other byproducts are your hydrogen chloride and aluminum trichloride. So, the Lewis acid that we are used initially is generated at last. So, what conclusion do we obtain? We obtain that aluminum trichloride is just used as the catalyst to initiate the reaction, and this mechanism of chlorination reaction is also similar to the mechanism of the bromination reaction. So, almost all the steps are equal. So, now let us consider that what happens when benzene is treated with excess halogen in presence of the Lewis acid. We are using chlorine in presence of Lewis acid, let it be aluminum trihalide. So, when benzene is treated with excess halogen, let the halogen is your Cl2, then what will happen? And another question is, what happens when we are using the aromatic hydrocarbon toluene instead of benzene? So, if toluene is subjected to halogenation, what will be the product? Now, you see that if excess of halogen is used, the second atom of halogen is introduced in the ring, and mainly at the ortho position as well as the para position. Why? Because the resonating structure of chlorobenzene indicates that the ortho and para positions have more electron density than the meta positions. So, that is why the electrophile, the second atom of chlorine will approach the ortho position or meta position with respect to the first atom or the first chlorine atom already attached to the already present in chlorobenzene. So, we are getting the mixture of orthochlorobenzene and parachlorobenzene. Similarly, what is the answer to the question number 2? That is, if toluene is used instead of benzene, what will be the product in halogenation reaction? So, toluene when treated with chlorine in presence of or halogen in presence of aluminum halide or anhydrous ferric chloride, then it produces the mixture of ortho and parachlorotoluene, provided the halogen is your chlorine, and if it is bromine, then you will get the orthobromotoluene and parabromotoluene. So, why we are getting the orthobromotoluene and parabromotoluene here? The reason is that like chlorine, the methyl group in case of toluene is also ortho and para directing, which already you have studied in the orienting influence of the different groups in case of aromatic compounds. So, now the question arises that whether it is possible to prepare the fluoroarenes by the direct halogenation, because we are preparing chlorobenzene and bromobenzene, but is it possible to prepare fluoroarene or fluorobenzene? But this is not possible. Why? Because the reaction of fluorine or fluorination reaction of benzene is violent because of the high reactivity of fluorine. Similarly, when we consider the iodination of aromatic compounds or hydrocarbons, then that iodination is also found reversible. That is not so smooth, just like your chlorobenzene and bromobenzene preparation. Then what will happen? So, since it is reversible, then the iodobenzene that you prepare, then again it gives back the aromatic hydrocarbon. So, our purpose is not fulfilled. So, what should we do so that we can prepare the iodobenzene? For that purpose, we have to carry out the reaction in presence of some oxidizing agents. So, what are those oxidizing agents? Those oxidizing agents are your nitric acid and hydriodic acid or mercuric oxide. Now, why we are using the oxidizing agent? That is because the hydrogen iodide that you obtain is behaving as the reducing agent. So, since it behaves as the reducing agent, so it reduces the iodobenzene to the aromatic hydrocarbon or the benzene. But when we are using the oxidizing agent, this oxidizing agent nitric acid or hydriodic acid, they combine with hydrogen iodide producing the iodine. But mercuric oxide when combines with hydrogen iodide, then it produces the hydrogen iodide with water. So, for this reason only the reaction, if the reaction is carried out in presence of the oxidizing agents, then the reaction will not be reversible or it is possible to prepare the iodobenzenes. So, Now, let us consider that what we have studied till now, that is in preparation. So, mostly we have discussed only the preparation of the haloarenes from benzene, that is by direct halogenation. So, in conclusion we can conclude that fluorobenzene formation is not possible, as it is a violent reaction because of the reactivity of fluorine. Similarly, the iodobenzene reaction being a reversible reaction, direct iodination is not possible. So, that is why it should be carried out in presence of some oxidizing agents, whereas the chlorobenzene and bromobenzene formation is possible by direct chlorination. So, let us I hope that you must have followed this much, that is about classification, nomenclature and also the preparation of halobenzenes or haloarenes by direct halogenation reaction. Students, now let us consider the preparation of haloarenes. Mostly we shall discuss the preparation of the side chain halogen derivatives or the aryl alkyl halides and also the preparation from benzene diazonium halide. Today we shall discuss this much. So, now let us see that how the side chain halogenation of benzene aromatic hydrocarbon is carried out. Now, let us consider the example of toluene. Now, when toluene is treated with chlorine in presence of sunlight and absence of the halogen carrier, then you see that you will obtain the benzyl chloride, that is a side chain substituted haloarene. So, toluene when treated with chlorine in presence of sunlight, but in the absence of the halogen carrier. Now, you know that in direct halogenation we are using the catalyst, that is your Lewis acid, maybe the anhydrous aluminum chloride or ferric bromide. But here in the preparation of side chain halogenation, there is no such halogen carrier is required. So, the reaction is simply proceeding by the general halogenation reaction followed in case of alkanes. So, the product is your first one is your benzyl chloride, but if the chlorine is present in excess amount, then the second hydrogen of the side chain is replaced, producing the benzyl dichloride, and finally, the third hydrogen is replaced and we obtain the benzo trichloride. So, this is the method of preparation of the side chain halogenation reaction, but the question arises that suppose the side chain is not the methyl group, let it be the ethyl benzene. So, if it is ethyl benzene, then which carbon or which hydrogen is replaced by the halogen, whether the carbon attached directly to the hydrogen attached to the carbon directly linked to the benzene nucleus or the CH3. For example, in ethyl benzene, as mentioned in the slide, you find that the carbon atom marked in red, that one is bonded to the two hydrogens. Now, by this halogenation reaction, these two hydrogens can be replaced, producing 1 chloro 1 phenyl ethane or 1 dichloro 1 phenyl ethane as the products. So, the carbon atom which one is directly attached to the benzene ring is known as your benzylic carbon, and therefore, the process is called the benzylic halogenation. Similarly, instead of chlorine, the halogenation of the side chain can also be carried out. So, what is the reagent? The reagent is your sulfuryl chloride, and reaction condition is 475 Kelvin in presence of light, and the trace amounts or little amounts of peroxide is used for the benzylic halogenation. So, toluene when treated with thionyl chloride or sulfuryl chloride at 475 Kelvin, it produces the benzyl chloride, and the byproducts are your that is your HCl, and also byproduct is your HCl and sulfur dioxide. So, now let us see the second method of preparation. So, this is all about your direct halogenation of aromatic hydrocarbons, but what about how can we prepare the haloarenes from benzene diazonium salts? Now, this preparation of haloarenes from benzene diazonium salts was first carried out by the scientist Sandmeyer, and the reaction is named as the Sandmeyer's reaction. So, in Sandmeyer's reaction mostly we are using benzene diazonium salt. So, benzene diazonium salt is the freshly prepared benzene diazonium salt. So, therefore, it is necessary to know that how the benzene diazonium salt is prepared. So, in general we can say that the Sandmeyer reaction involves two steps. The step 1 is the formation of the benzene diazonium salt, and the second step is preparation of the haloarene from the corresponding benzene diazonium salt. So, the step 1, which one is the benzene diazonium chloride preparation or benzene diazonium halide preparation. For that purpose, we are following the diazotization mechanism. So, what is that? Now, in that case, the primary aromatic amine, let it be aniline, that one reacts with sodium nitrite and the halo acid to form the diazonium salt, and the diazonium salt is your benzene diazonium halide. For example, if we treat aniline with sodium nitrite in presence of hydrogen chloride at the temperature 0 to 5 degree centigrade or 273 to 278 Kelvin, then you will obtain benzene diazonium chloride. Now, the benzene diazonium chloride is our prepared. So, what is the second step? Now, the second step is how to prepare the haloarene, that is maybe the chlorobenzene or the bromobenzene from this benzene diazonium halide. For that purpose, the freshly prepared diazonium salt you are prepared in the first step is treated with cuprous halide or cuprous halide, and this cuprous halide may be your cuprous chloride with hydrogen halide or hydrogen chloride for the preparation of chlorobenzene, or the cuprous bromide in presence of hydrogen bromide to produce the bromobenzene. So, in general we can write that benzene diazonium halide as shown in the reaction, that benzene diazonium halide treated with cuprous halide producing the aryl halide. Here the halide X may be your chlorine or bromine along with the liberation of the nitrogen. So, what is your benzene diazonium? For example, for chlorobenzene and bromobenzene, what are the reactions? Now, here are the reactions, that is benzene diazonium chloride is treated with cuprous chloride producing the chlorobenzene, and benzene diazonium chloride when treated with cuprous bromide, it produces the bromobenzene. So, now question arises that direct fluorination is not possible. So, we cannot prepare fluoroarenes by direct fluorination or by direct halogenation. However, the fluoroarene can be prepared from benzene diazonium salt. So, what is the benzene diazonium salt used for the preparation of fluoroarene? The benzene diazonium salt that we are using is your diazonium tetrafluoroborate, and this diazonium tetrafluoroborate is obtained by the diazotization of aromatic amine or aniline with the aqueous sodium nitrite in presence of fluoroboric acid with formula HbF4 at 273 to 278 Kelvin. So, this is the reaction for the preparation of diazonium tetrafluoroborate, and this diazonium tetrafluoroborate on simply heating produces the fluorobenzene. So, no other reactant is required here, simply by heating the diazonium tetrafluoroborate we can prepare the fluorobenzene. So, this is the advantage, we can prepare the fluorobenzene from benzene diazonium halide, whereas the fluorobenzene cannot be prepared by direct halogenation of benzene. Similarly, in case of iodobenzenes or iodoarenes, we can also prepare these compounds from the benzene diazonium salt. So, what is the reagent we are using here? Now, simply by shaking the benzene diazonium halide potassium aqueous potassium iodide, we can obtain the iodobenzene. So, iodobenzene is obtained by shaking benzene diazonium halide with aqueous potassium iodide. So, these are the different steps or different methods and reaction conditions required for the preparation of fluorobenzene, chlorobenzene or fluoroarene and bromoarene, chloroarene and iodoarenes from benzene diazonium halide, or this is all including that is your Sandmeyer's reactions. But another method of preparation of haloarenes, mostly the chlorobenzenes or chloroarenes and bromoarenes, is by the Gattermann reaction. So, what is the difference between this Sandmeyer reaction and Gattermann reaction? In Sandmeyer reaction, we are using cuprous halide with the dissolved in the hydrogen halide or the halogen acids, whereas in case of Gattermann reaction, instead of using the cuprous halide, we are using only the copper powder. So, this is simply the modification of the Sandmeyer reaction, and the mixture of freshly prepared copper powder in the presence of corresponding halogen acids is used for the preparation of the haloarenes. So, if we are interested to prepare chlorobenzene, then we have to use copper powder in presence of hydrogen chloride. If we are interested to prepare bromobenzene, then we have to use the copper powder with hydrogen bromide, and these are treated with the starting material is your benzene diazonium halide. So, the reactions are, that is your this one, that is benzene diazonium chloride is treated with copper in presence of HCl and it produces the chlorobenzene, and by simply heating benzene diazonium chloride with the cuprous bromide copper powder in presence of hydrogen bromide produces the bromobenzene. Again you see that benzene diazonium chloride on heating with copper powder in presence of HCl produces chlorobenzene, and benzene diazonium chloride on heating with copper in presence of hydrogen bromide produces the bromobenzene. So, this is the difference between the Sandmeyer reaction and the Gattermann reaction. That is what I have discussed, that is the chloroarenes and bromoarenes can be prepared by treating the diazonium salts with cuprous chloride or cuprous bromide dissolved in HCl or HBr or in hydrogen chloride or hydrogen bromide. But in case of Gattermann reaction, the chloroarenes and bromoarenes can be prepared in a mixture of freshly prepared copper powder in presence of corresponding halogen acids with the diazonium salts. So, this is the difference between the chloroarenes and the difference between the Sandmeyer's reaction and the Gattermann's reaction. So, now let us have a look upon the different methods that we have discussed here for the preparation of the haloarenes. So, first we have prepared or discussed, that is how the side chain haloarenes are prepared, and for side chain haloarene preparation the halogenation method is similar to the halogenation of alkenes. There the reagent is your chlorine or chlorine in presence of the sunlight and no halogen carrier is required. Similarly, for Sandmeyer's reaction, the reactions for the preparation we are using the starting material, that is benzene diazonium salt, and benzene diazonium salt when treated with the cuprous halide in presence of halogen acids, we are mostly preparing the chlorobenzenes and the bromobenzenes. But when the fluoroarene preparation comes into our mind, then the reagent which we are using or the starting compound is our benzene diazonium fluoroborate. So, benzene diazonium fluoroborate is prepared by the diazotization of primary amine, and instead of using the HCl we are using the fluoroboric acid. So, that we are getting the fluoroarenes, and the fluoroborate upon heating produces you the fluoroarenes. Similarly, for iodoarenes or iodobenzenes, the benzene diazonium halide on simply shaking with the halogen simply shaking with the potassium iodide produces the iodoarenes. So, this is all about your preparations, and then we discussed that what is the difference between the Gattermann reaction and Sandmeyer's reaction. These two are mainly the mainly to differentiate the preparation of chlorobenzene and bromobenzenes mainly by the reagent that we have used. The reagent means which reagent is used in Sandmeyer reaction, that is the cuprous halide, but in case of Gattermann reaction, in place of cuprous halide we are using only the copper powder. So, by this process we can differentiate that how we can prepare the different compounds or the different categories of haloarenes, that is side chain as well as the nuclear substituted haloarenes. So, Sandmeyer's method or preparation of the haloarenes from benzene diazonium chloride has the advantage that from benzene diazonium chloride we can prepare almost all the types of the haloarenes which is not possible by direct halogenation. So, this is the advantage of the haloarenes. So, now let us consider our purpose will be that if this is the method of preparation of haloarenes, then why we are interested in preparing all these compounds? Because these compounds are having lot of applications in our day to day life. As you know that mostly we are using the DDT, that is your insecticide, some fungicides, some disinfectants, and all are prepared from these haloarenes. So, therefore, we have to consider that how these compounds are prepared. Since the starting compound is your haloarene, for the preparation of the articles used in our day to day life, it is necessary to study the details of the preparation of these haloarenes. So, I think that you must have understood the preparation by different methods. Students, let us come to the physical properties of haloarenes. In this section, we shall discuss what are the common properties of the haloarenes, that is, what is the variation of melting point, boiling point, density and behavior towards the solvents, as well as the stability of the haloarenes, and how does the haloarenes are applicable in our day to day life because of their physiological activities. So, the physical properties are, these are the colorless oily liquids or relatively low melting point solids, and the second point is that they are insoluble in water due to their low polarity. You all know that like dissolves like. So, what is that like dissolves like? Like dissolves like means the polar solvents dissolve the polar compounds and the non-polar solvents dissolve the non-polar compounds. So, being water is a polar compound, but because of their low polarity of the haloarenes, they are less soluble in case of the polar solvent like water. However, they are soluble in the common organic solvents like your ethanol, diethyl ether, and their density is greater than 1. When the density of water is nearly 1, then density of the haloarene is greater than 1, and the if we make a comparison with the melting point, boiling point and density values, it is found same aryl group. That is, if the aryl group is same, but we are changing the halogen atoms, then what will happen? Now, these physical properties, that is your melting point, boiling point and density, they gradually increase as we move from fluoro to the iodo compound, which you can better understood from this table. Now, you see that in case of fluorobenzenes, the melting point is -42, whereas for chlorobenzene it is -45. These are in degree centigrade. So, chlorobenzene is -45, for bromobenzene it is -31 and -30. Similarly, for boiling points you see the gradual rise in the value of the boiling point and also in the density. So, these properties gradually rise as we change only the halogen atoms and the aryl group remains the same, that is the phenyl group. So, next one is that is your the variation. If we consider the dihaloarenes, then what will happen to their physical properties? Now, in case of isomeric halides, dihalides, that is your ortho, meta and para dihalides, it is found that their boiling points are so close that we cannot separate these isomers by distillation methods, because distillation method is the method, fractional distillation is the method by which we can separate the compounds only by differing in their boiling points, because when the boiling point of one compound is attained, that one is separated. After that, the higher boiling point compounds get separated, but if the boiling points are so close, then it is difficult to separate these compounds. That means, over a range minimum certain difference is required for the separation of the compounds from the by the fractional distillation. But if we compare the melting points, then you found that melting point of the para isomer is greater than that of the ortho and the meta isomers. So, why the para isomer has the greater melting points? Now, you see the table that is given in the slide, that dichlorobenzene, ortho dichloro, meta dichloro and para dichlorobenzenes are given. Now, you see that the boiling points is for ortho dichloro is 453, for meta dichloro it is 446 and for para dichloro it is 448 Kelvin. So, in case of melting point, for ortho dichloro it is 256 Kelvin, for meta dichloro it is 249 Kelvin and for para dichloro it is 323 Kelvin. So, why the melting point? If you compare the boiling point, you see that these are very close to each other, that is 453, 446 and 448, all are almost nearly equal, whereas in case of melting point you see that para dichloro has higher melting point, that is 323 degree. So, why the para isomer has the higher melting point? The reason is that in para isomer the molecule has the symmetry, and because of this symmetry it fits well in the crystal lattice as compared to the ortho and the meta isomer. So, next arises what about the stability? Now, if you compare the stability, then you see that stability of the haloarene is depending upon the strength of the carbon halogen bond. Now, as the strength of the carbon halogen bond decreases in the order, that is carbon fluorine bond is more stronger than the carbon chlorine, than the carbon bromine and carbon iodine, then the stability of the haloarenes having the same aryl group decreases from fluoride to corresponding iodide. So, which one will be more stable? Now, the more stable is your fluoroarenes, whereas the bond strength decreases as the order. So, the stability of haloarenes decreases. Similarly, the haloarenes have the physiological activity. So, what are those? Now, that is they are used as insecticides, for example, used as DDT, and germicides like your hexachlorophene as a disinfectant for skin used in the soaps, and para dichlorobenzene which is used in the mothballs, that is to prevent the insects, entry of the insects. So, now let us have a look upon the certain questions arises in our mind basing upon these physical properties, that is why solubility of haloalkanes in water is very low, but are soluble in organic solvents. Solubility of haloarenes in water is very low. Now, solubility of haloarenes in water is low, that is mainly due to the absence of the hydrogen bond. Similarly, another question is given that which isomer of chlorobutane will have the lowest boiling point and which has highest. This obviously, this is a question from chloroalkane, but here you can say that basing upon the degree of branching, with increase in the degree of branching, the boiling point value increases. So, this is the answer, that haloarenes are insoluble in water because they cannot form the hydrogen bonds, and the isomer, that is 2-chloro-2-methyl propane, has high boiling point as the branched molecule having the spherical shape, weaker interparticle force to so lower the boiling point. Now, the another question is what is the use of DDT? Obviously, it is used as the insecticide. Then what is the reaction between benzene and chlorine in presence of acid is carried out? Then which one is the attacking species? The attacking species is the electrophile, that is the chloronium ion. So, what are the halogen carriers used in the preparation of haloarenes? Now, the haloarenes, the halogen carriers that we are using in halogenation of arenes or halogenation of benzenes is the Lewis acids like your anhydrous ferric or aluminum halides. So, now let us come to just memorize the things that we have discussed, that is we have discussed here the preparation of chloro and bromobenzenes from benzene, preparation of fluorobenzene by direct halogenation is not possible, and why we are using the oxidizing agents like the nitric acids or hydriodic acids for the preparation of benzenes, iodoarenes, and how can we prepare the haloarenes by Sandmeyer's reaction. What is the basic difference between the Sandmeyer's reaction and Gattermann reactions, and what is the physical properties variation or variation of the physical properties of the haloarenes. So, students, we have discussed how to prepare the haloarenes and what are their physical properties, and in this portion we have discussed the preparation of haloarenes by direct halogenation from benzene diazonium chloride or benzene diazonium halide or benzene diazonium salt, as well as we have considered the preparations mostly the properties and mostly the physical properties, not the chemical properties. So, what are those physical properties and what is their variation in the different haloarenes, that one is discussed, that is how the property varies when the halogen atom is changed. So, I think that this portion, that is your preparation and physical properties of haloarenes may be that we have discussed here may be helpful for us or beneficial for you, and also thank you very much for being with me during this session. Thank you all.